Okay, in this video, we're going to prove that intervals are connected. So the theorem is every closed interval from A to B is connected. So intuitively, of course, we would expect this to be true. So the idea behind the proof, well, we want to show that this interval cannot be written as the union of two disjoint non-empty open subsets. So the idea is, suppose that A is a non-empty subset of this closed interval that is both open and closed. So what do we want to show about it? Well, we want to show that A is the entire closed interval, right? And the idea is, since A is closed, so since A is closed and bounded above, it has a supremum. Now, one thing I should probably mention is that this is A is a closed subset of R, because A is closed. So A is a closed subset of a closed subset. So if you have a closed subset of the closed interval AB, okay, it's closed in R. So one way of putting it is, so this is a general fact about closed sets. So since A is closed in the interval AB, and this set is closed, this interval is closed, A is closed in R. So remember, what it means to be closed in R means that it's closed in the metric space R. So it's one of the closed subsets of the metric space R. Because closed is relative to the metric space, right? So if you have a closed subset, this is just a review. If you have, let's say you have the open interval from A to B, okay? And let's say that you have this half-open interval from A to, say, C, and it contains C. Well, this subset is closed in the open interval from A to B because it's the intersection of a closed subset of R with the open interval from A to B. But A, so even though this, let's call this an A. So even though A is closed in the open interval, A to B, it's not a closed subset of R. So you have to be careful when talking about closed sets. So there's the general fact that if you have, so if instead of, say, the open interval from A to B, you had the closed interval from A to B, and you take a closed subset of this, so that means it's the intersection of a closed subset in R with the closed interval A to B, okay, this subset is closed in R. So that's just the reminder. Okay, so A is closed in R, so you have a closed subset, and since A is bounded above by B, it has a supremum. A has a supremum. Okay, right? Because every bounded non-empty subset of real numbers has a supremum. But moreover, since A is closed in R, the supremum must be in A. So just a reminder that saying that A has a supremum means that there is a least upper bound of A, but saying that A has a supremum doesn't mean that the supremum is actually an element of A. But since A is a closed subset, the supremum must be in A. So since A is closed, the supremum of A is an element of A. Let's review why that's true. Okay, because basically, so you have a closed subset A. So if the supremum were not in A, okay, so if the supremum of A were here, then since the complement of A is open, there is some ball of radius, say epsilon, some epsilon, such that that entire ball is contained in the complement of A. But then there would be, if you take, say, this element here, which is like the supremum of A minus epsilon over 2, that would be an upper bound of A. It's an upper bound of A because it's greater than every element of A. Remember, this epsilon ball is completely outside A, right? So that's just a reminder of how that works. So supremum is an A, but now the idea is that the supremum of A must be B. So why must it be B? So we claim that the supremum of A is B. So the proof of this is suppose that it weren't. Say the supremum of A is C, with C strictly less than B. Well, here's where we use the condition that A is open, because let's say B is here and C is here. Okay, so your supremum, say C, is in A, right? But since A is open by hypothesis, then it contains some ball centered at C. But then, do you see where the contradiction would be? You would have an element here which is greater than, what am I saying? Let's see, if C were the supremum, then that means it's greater than or equal to every element of A. But since A is open, then there is some ball centered at C that is completely contained in A. So this is a subset of A. But then that would mean that C is not a supremum because there are elements here that are in A that are greater than C. Okay, so let's write that down. So suppose not, say supremum of A is C with C less than B. So since A is open, there is an open ball centered at C that is contained in A. But such an open ball must contain elements that are greater than C. Contradicting C being the supremum. Okay? So the supremum of A is B. Well, I claim we're done, because what we showed is that whenever you have a non-empty subset of this closed interval, AB, that is open and closed, the supremum is B, right? So and therefore B must be an A. So So that we proved the claim, so we conclude that B must be an A, because B is the supremum of A, and we know that the supremum of A is an element of A since A was closed. But if you think about it, we just showed that whenever you have a non-empty open and closed subset of the closed interval, it must contain B. So therefore, okay, how do we finish? You cannot have two disjoint non-empty open and closed subsets of the closed interval AB because they both must contain B. So they cannot be disjoint, right? So that's the proof. Okay, so therefore, any two subsets, any two non-empty subsets of the closed interval AB that are both open and closed cannot be disjoint because, well, there's a little too many therefores, so, well, whatever, it's fine as it is. Therefore, any two non-empty subsets of the closed interval AB that are both open and closed cannot be disjoint because they both must contain A. It turns out they both must contain A also, but they must contain B. So, therefore, this closed interval is connected. Okay, that's the proof. And so, therefore, any closed interval is connected. And we can actually use this to prove a more general fact, which is, so more generally, we have a corollary, which is that any open interval of R is connected. Any R itself is connected. And actually, more generally, any subset S of R that contains all elements between two given elements in the set. So any subset S of R that contains all elements between any two elements of S is connected. So for instance, every open interval has the property that whenever you have two elements in the open interval, it must contain all the points between those two elements. And the real number line also has this property. Okay, so the proof is, so we have this set. Well, first of all, if S contains only one element, we're done, because a one element set is connected. Let's think about why that's true. Because there are only two subsets, the empty set and S, right? So saying that any S being connected means that any other, let's see. Okay. Saying that S is connected means that there are no other non-empty subsets that are both open and closed, but there are only two subsets, right? So there aren't even any other subsets to begin with. So therefore, a one element subset is connected. Okay, so maybe we should write that down. So if S consists of a single point, S is connected because the only subsets of S are the empty set and S. Okay, so we can assume that S has at least 2 points. So suppose that S has at least 2 points, 2 distinct points, A and B. Well, by hypothesis, S contains all the elements between A and B, so S contains the closed interval from A to B. And we want to show that S is connected. And we have some subset that we know is connected. So suppose towards a contradiction that we can write S as A union B, where A and B are non-empty, open, disjoint subsets of S. Then we intersect it with the closed interval from A to B. So the closed interval from A to B is the intersection, it's the union of the intersection with A and the intersection with B. But these two sets are open in the interval in the closed subset AB, right? These two sets are by definition open in the closed interval from A to B because an open subset of this interval is the intersection of an open set with the interval. So this expresses the closed interval as the disjoint union of two non-empty okay, why is this non-empty? Yeah, that's an interesting point because you could have S being, say, A and B, and then the closed interval from A to B like this, right? Let's see, suppose that S is the disjoint union of A and B. Yeah, I think we need to guarantee that little a is in capital A and little b is in capital B, or something like that. Let's see. Yeah, we have to change the proof a little bit, don't we? So I think we should say, suppose that S is the union of A and B. Okay, I think we should change this to let little a be an A and little b be an B, which is fine because capital A and B are non-empty. So these are in S, therefore the closed interval from A to B is in S. Yes, this would be correct. So, okay, sorry, we have to change the proof a little bit. I think we actually, even though these are true, we probably don't need these statements, right? Suppose I think we should suppose that S is the union here, and then we take little a and little b and B, then this closed interval, by hypothesis, and one of them is less than the other, so we suppose that little a is less than little b, then the closed interval from A to B is a subset of S, and also it's the intersection of A union the intersection with B, and that expresses the closed interval as the disjoint union of two non-empty open subsets of the closed interval from A to B, contradicting the connectedness of the interval. Okay, this proof is correct. Okay.